Okay, so this video is going to wrap up section 4.2 for us, and this is where we're going to talk about the second derivative test for extrema. And we're going to go ahead and use an example here to illustrate both the second derivative test and the first derivative test. Okay? So the problem we're going to examine here is, I wouldn't say a challenging problem, but it's definitely probably more of the challenging ones than the ones we've looked at so far. So let's look at f at x is equal to x e to the negative 0.1x, and we're going to find the critical numbers, find relative extrema, using f prime at x, and then we're going to find relative extrema using f double prime. And now it doesn't matter on a homework problem or a quiz or an exam whether you use the first derivative to determine whether you have a relative extrema or whether you use the second derivative to determine whether you have a relative extrema. Both have their advantages and disadvantages. The first derivative has its advantage of you only need the first derivative. The second derivative one has its advantage that you only have to plug in one number. So let's go ahead and see what we have here. So first off, we need to find the critical numbers. Well, we aren't given a domain in this problem, so we should write down what the domain here is. And of course, this domain here is all real numbers, because I've got x, which is defined for all real numbers, and e to the negative 0.1x, which is defined for all real numbers. Alright, so then we need to find my first derivative. Now, we should be getting kind of used to doing these product rules and other things like this. So this would be, using the product rule, the derivative of the first, so it'd be the derivative of x times e to the 0.1x plus x times the derivative, I'm sorry, this is negative 0.1, e to the negative 0.1x. And so this would be equal to, well, derivative of x is just 1, so e to the negative 0.1x plus x times, and then I'd have negative 0.1 coming down from the chain rule, e to the negative 0.1x. And so my f prime at x would be e to the negative 0.1x minus 0.1x e to the negative 0.1x. And I'm going to go ahead and factor that e to the 0.1x out, or the e to the negative 0.1 I should say. So I'd be left with e to the negative 0.1x times 1 minus 0.1x. Alright, so that's my first derivative. Now, part A, I'm trying to find the critical numbers. So we know I set my derivative equal to 0. And we've done a problem like this as far as finding critical numbers, I believe last week, but I want to emphasize again here. This term right here is never 0. So we get no critical numbers from it. So all I have to examine, of course, is this term. And I'll go ahead and write it over here. We need to determine when is 0 equal to 1 minus 0.1x. I'll skip the solving of it, but if you solve it, you get x equals 10. So my critical numbers for part A, since my domain was all real numbers, my critical numbers are x equals 10. Now part B is asking to determine whether this is a relative extrema or what kind of relative extrema this is. And this is actually something that's called the first derivative test. We've never named it, but it's called the first derivative test because you're using the first derivative. And basically all we're going to do is create a sign diagram with increasing and decreasing. All those examples where we found functions increasing or decreasing really was leading to this. So I'm going to put my little number line here. I'm going to put 10 in here. And then I'm going to pick things to the left and to the right of 10 and figure out what they are. So since I can pick anything to the left of 10, I'm still going to pick an easy number to start with. So I'm going to test x equals 0. Now remember, I'm testing this in the first derivative. So I'm looking at f prime at 0, which would be e to the negative 0.1 times 0 times 1 minus 0.1 times 0. Well, e to the 0 would be 1, and this would be times, well, that would just be 1. So this is positive 1. And again, I'm just emphasizing the fact that it's positive, which we know that means we are increasing. Now I have to substitute in a number to the right of x equals 0. So, or not x equals 0, x equals 10. Substitute something into the right. So I'm just going to go ahead and test x equals 11. And so we'd have f prime at 11 is equal to e to the negative 0.1 times 11 times 1 minus 0.1 times 11. So this is going to be e to the negative 1.1 times 1 minus 1.1. Now, I'll go ahead and write what this number is, but I claim you don't need to. You can actually figure out whether it's positive or negative, because an exponential, that's always going to be positive. It might be a small number, but it's always going to be positive. And then this one here is clearly negative. So I'm going to get a negative answer out. But let's go ahead and do that on the calculator. So give me a second to punch this into my calculator. And when I punched this into my calculator, I got this was approximately negative 0.0333, rounding it. Which of course is a negative, which is what we said it was going to be, which means I'm going down. So now we know what x equals 10 corresponds to. We've just applied the first derivative test because we've looked at something to the left of 10, something to the right of the 10, determined that I'm going up, and then I'm going down. So clearly I have to be hitting a hill. And I'm just going to kind of do a little dotted line here. So I have to be hitting some kind of peak value here. I don't know it looks exactly like the dotted blue line that I've drawn there, but I'm hitting some peak value. So I know that x equals 10 corresponds to a relative maximum. Now the problem didn't actually ask us to do this, but let's go ahead and do it in this case. What is the maximum? Well, that's where you would go back. We know that x equals 10 corresponds to a relative maximum. That's where we would need to go back into the original equation and plug in 10. And so we'd have f at 10, which would be 10 e to the negative 0.1 times 10, which I need to, again, punch into my calculator here. So just a second. And you get that this is equal to 3.68 if you round it. So the maximum again here, this is my relative max. X equals 10 corresponds to the location of my relative max. All right? All right, so that's using the first derivative test, and a lot of people like this one. It's a fairly easy one to understand. Not a lot of work necessarily involved, but you do have to plug in two numbers. The best thing about this technique is that you only need to know the first derivative. So let's look at the other technique for determining whether I'm at a min or a max, and this is using the second derivative. Well, of course, I'm going to need the second derivative, which we'll get in a second here. But before we do that, let's talk about what's going on here. So the second derivative here, well, we know that this tells me about concavity. And let's think about this. If we have a critical number, we're going to just assume that we're in the case f prime at x equals 0, because technically it could be undefined. Okay, so we have a critical number and we're at f prime at x equals 0. So we know my tangent line is a horizontal line. Alright, so my tangent line is a horizontal line. Second derivative, concavity. So if we were to evaluate f double prime at the critical number, this will tell me the concavity at the critical number. What does that mean? It's going to tell me the concavity at the critical number? Well, let's just do an example here with a picture here, and then we'll get back to this example problem here. Well, suppose f double prime at x at the critical number is greater than 0. So if it's greater than 0, what does that mean? We're concave up, right? But then at the critical number, we know that I have a horizontal tangent line. So the critical number has to be right down here. And so this is my critical number. And what do we just know here? Well, we know that this has to be then, just based off this little picture I drew, this corresponds to a min. Alright, so that's just kind of giving you a little bit of background on how to do this. So now let's get back to the problem. So back to example. So we know that my critical number is x equals 10, and I'm going to go ahead and write down what my first derivative was. My first derivative was e to the negative 0.1x times times 1 minus 0.1x. Now, this is where the disadvantage of the second derivative test comes from, is that you need a second derivative. So I have to take another derivative here, which means I'm going to need to do another product rule. So this would be the derivative of the first times the second plus the first times the derivative of the second. Alright, so let's go through and do those derivatives. So you'd have negative 0.1 e to the negative 0.1x times 1 minus 0.1 x plus e to the negative 0.1x times derivative of 1 minus 0.1x would be negative 0.1x. Okay, so let's go ahead. I'm going to factor out the e to the negative 0.1 here. So we'd have negative 0.1 times 1 minus 0.1x minus, and actually I realized I wrote something wrong here. The derivative of 1 minus 0.1x is just negative 0.1. So then this would be minus 0.1. And then simplifying this out just the tiniest bit more, we'd get negative 0.2 minus 0.01 x. So that's my second derivative. You can kind of see where the disadvantage of the second derivative test comes in, is that in this function, even though this wasn't what I consider complicated, you have to spend the time finding a second derivative. So really, the second derivative test I only employ when it's a function that it's really quick to take a second derivative of. For instance, like a polynomial function. But we do have it now, so now we're going to evaluate critical number. We're going to evaluate f double prime at x at critical number. And so we'd have f double prime at 10 would be, of course, it's going to be e to the negative 0.1 times 10 times negative 0.2 minus 0.01 times 10. And again, we can determine whether this is positive or negative just by inspection, but I'll go ahead and compute it out. So we have e to the negative 0.1, sorry, e to the negative, I can't do my arithmetic right now, e to the negative 1, and then we've got negative 0.2 minus 0.01 times 10, so this would be negative 0.21, I believe. And throwing this back into my calculator real quickly. I get that this is, rounding it, negative 0.0773. And again, the key thing here is that this is negative. So what does that mean? It means at critical number, we are concave down. So what does that give me, a max or a min? Well, the easiest way is just draw something that's concave down. That's concave down, and that's where my critical number would be, because it's got the horizontal tangent line. Oh, so we have a relative max, which is what we got from the first derivative test. So we know that x equals 10 corresponds to a relative max. Alright, so this marks the end of section 4.2. So there's a lot of information in 4.2. We had increasing and decreasing, concave up, concave down. We have these first derivative tests, the second derivative tests. I hope to be back on Friday, but check your email in case I'm not. And I was going to say here, one other thing. Oh, we are going to be skipping section 4.3 in the text, and on Friday we will be starting section 4.4, which deals with optimization.